Okay, today we'll be learning numerical integration with C++. Okay, want to make sure that it is. Okay, so numerical integration. Okay, so integration. Okay, in mathematics, the definition is the area under the curve, right? So let's say you have a curve. Okay, function. Let's say y equal to fx. Okay, so y is a function of x, and then if you want to integrate, okay, from x1, okay, to xn, okay, so integration means that the area, okay, under the curve from x1 to x number n, right? But then you have learned integration, okay, in your mathematics, right? But then a lot of time, okay, we have very complicated mathematics functions, okay, which cannot be determined mathematically, okay, in a easy way. So what we can do is we can use programming to help us to do integration using approximation. Okay, so the approximation technique that we are using is using trapeziums. Okay, we will use a lot of trapeziums, okay, to fill up the area under the curve. Okay, and then we calculate. Then we will need to define, okay, the width of the trapezium. Okay, so that the area under the curve is filled, okay, by these trapeziums, small enough trapeziums, okay, to get an approximate results with good accuracy. Okay, so if you from this chart here, if you see, we reduce the size of the p. P is this, okay, the width of the trapezium. Okay, we can increase the accuracy. Okay, and then the total area under the curve, okay, between xi and xn is the sum, okay, of the area of all these trapeziums. Okay, so the strategy is simple. Okay, now we need to, since we are calculating the trapezium, okay, the area of the trapezium, then we need to use this trapezoidal rule. Okay, so the equation is simple. Okay, the area of trapezium is simply, okay, half of the width or height of the trapezium, okay, times the shorter and longer sides of the trapezium. Okay, so if we come back to this chart, so this is like the shorter edge is this one for this trapezium, the first trapezium here, the shorter edge, okay, plus the longer edge times p, okay, times half. Okay, and then the area for the second trapezium is this fx, okay, this value fx plus this value, okay, xi plus 2, okay, plus this value times p. Okay, so the width of this trapezium is also p. Okay, then times 1/2. Okay, and then you do the same for this trapezium as well, and then you sum the area, you sum them up, then you get the approximated value, okay, of the area under the curve, okay, between this x and this x here. Okay, so the strategy is simple. So if you want to get a more accurate result, okay, we will need to reduce the size of p, right, the size of the width of this trapezium. Okay, so then it means that when we reduce this one, we will need more trapezium to fill up the area. Okay, so let's say if you want to reduce it, you want to fill up this area with thousands of smaller trapeziums, meaning that this p will become very small. Okay, that by doing so you get a very accurate approximation, right? So we have seen the strategy on how to calculate the area under the trapezium. Now we will need to program, okay, the procedure to calculate the integration in C++. Okay, so the first thing is you need to call out this include IO stream, okay, for input and output. Then include, okay, include CMath, okay, and then we will need to do this using namespace std, like that, okay. So the next thing we need to do is we need to construct the polynomial, let's say, okay. So so there are a few things you need to get from the user, okay. So the first thing is the user needs to define, okay, the degree of polynomial, okay, define degree of polynomial, okay, and then you need to define, okay, the polynomial constants, okay, polynomial constants, okay, and then he will need to tell, okay, with this function, okay, he wants to integrate from what value to what value, right? From x1 to xn, right? So you need to define, okay, integration, okay, from x is equal to a to x is equal to b, for example. Okay, so you need to tell, okay, so you need to tell what is x1, okay, and this is what is xn. So x1 I'll say it, I'll define it as a, and then xn I'll define it as b. Okay, you need to define that. Okay, and then after that we'll do integration. Okay, so these are the steps. The first, you need to define degree of polynomial, define polynomial constants, define integration, okay, from xa to b. Then we need to construct polynomial, okay, construct polynomial, and then do integration, okay, and then print out results. Print out results. Okay, so these are the steps. We'll come back to refine these steps, okay, while we progress. Okay, so if you look at this step number 1, okay, define a degree of polynomial. So you need to use cout, okay, cout, okay, and ask user to define the degree of polynomial, right? Define degree of polynomial, okay, and then the user will have to key in, okay, cin, okay, and then you say the degree of polynomial, okay. To use degree, I will need to declare polynomial degree as integer degree, okay. Then after that you need to, the second step, define the polynomial constants, okay, cout, okay, define polynomial constants, okay. So we need to use these constants to construct our function, right? So this is e and dl here, okay, and then so maximum constants, okay, maximum 10 degree, okay, So maximum 10 degree. So maximum degree of polynomial he can construct is 10 degree. Okay, 10x. So we'll start from what is that? X0, a0. Okay, plus if we go to this one, okay, polynomial functions. Okay, y is equal to a0 plus a1 to the power of 1 plus a2, x power of 2 plus a3, x to the power of 3. Okay, until x to the power of 10. Okay, so if it is a n degree polynomial, then we will have n plus 1 constants. Okay, so n degree of polynomial, we have n plus 1 constants. We have 10 degree of polynomial, then we will have 11 constants. Okay, because a0 is there. a0 is also a constant. Okay, so this one, okay, we need to use for loop. Okay, so we have maximum 10 degree, then the maximum constants. Okay, your what is that, array can hold is 11, right? So we need to declare, okay, an array to hold those constants. So I will define a, okay, 11, like that. Okay, so this means a is a matrix, is an array. Okay, this array has 11 elements. It can hold 11 values. Okay, so I'll need to use for loop. Okay, for loop here to get the user to input the what is that, the values for each constant. Okay, so I'll need to use I starts from 0. Okay, integer I starts from 0, and then I less than equal to degree, right? I plus plus. Okay, so a, you need to key in Cin, okay, a of I, right? So for each loop, okay, you need to print out input, this should be a string, input value for a, okay, I AI, like that. Okay, so let's print out, let's try to program, okay, before we proceed further. So define degree of polynomial is a 3-degree polynomial. So define polynomial constants, maximum 10 degree. So input value for a0, I would say 1, 2, and 3, 4. Okay, so 3 degree, 4 constants, right? Then hit enter. Good. Okay, so my polynomial is like what is that? 1 plus 2x plus 3x squared plus 4x power of 3. Okay, so this one is done. Okay, the second step is done. Okay, and then define integration from xa to xb. Okay, and then you need to get the user, okay, to tell us, okay, he wants to integrate from what value of x to what value of x. So this one you can do it this way. What is that? Cout, okay, cout input integration range from what? Okay, like that, and then Cin, you read the value and put it in a, right? So this one you have to define it float, okay, A and B, right? You read the value and put it in A, okay, and then C out, input, integration, okay, range 2 to what value, okay, and then C in, send it to B. Okay, what is wrong with this guy? Like that. Okay, yes, so this one, okay, A, I'll need to change it a little bit, this one for A and A, like that. Okay, because the small letter A has been declared what is that, an array, okay, here. So when I declare it again, so it gave me error. Okay, so I need to change that one. So float A and B. Okay, so float A and B will be the range, okay, A and B here. Okay, so the next one, the next thing, okay, so this part is done. Okay, then we need to construct the polynomial. Okay, so we need to print out the polynomial. So we need to use for loop, okay, to print out the polynomial that we constructed. Okay, so I'll use integer I starts from 0, right? I less than less than or equal to degree, okay, and then I plus plus, and I plus plus. Okay, so so for this one, okay, I'll need to print out the function, okay, C out function f(x) is equal to, right, and then here, okay, is equal to y, no, what is that, C out, okay, a ai, sorry, ai, okay, times x, okay, to the power of I plus like that. Okay, so if we try to run the program, okay, define polynomial 2 degree, input 1, 2, 3, range from 1 to 2. Okay, so our fx is 1 times x power of 0. Okay, so this would be 1 plus 2x plus 3x squared plus nothing. Okay, so if I want to make it a little bit tidier, so I will need to use if else. So if I is equal to 0, okay, and then I print out AI only. AI okay, I need to copy this one, okay, and then put it here. Okay, AI plus, right, and then else if, okay, I is equal to degree, okay, so that's the last part. Hold on, right, like that. C out, C out is this one without plus and E and DL. Okay. Otherwise, if it is between I equal to 0 and I equal to degree, okay, you need to print out this one with a plus, right? So you have to put a plus there in between. Okay, so if we run the program again, let's check. So define degree of polynomial second degree 1, 2, 3, range from 1 to 2. Okay, now we have what's that, tidier function. Okay, so f(x) is equal to 1 plus 2x power of 1 plus 3x power of 2. Okay, x power of 1 is x actually, right? Right, so we have a function, okay, like that. Okay, the next thing we need to do is we have done the construction of polynomial. Now we need to do integration. So this integration part, okay, we need to define a few things, right? We need to define, okay, the width of the trapezium. Okay, so we need to define the width of the trapezium, or we can define how many trapeziums we need to fill up this area. Okay, so what we can do is we can use let's say we define, okay, I want 3 trapeziums to fill up this area. Okay, then P we can calculate by using these xn minus x1 divided by 3, right? And then the x0 will be the first value, okay, the first value of x should be this value a, this should be b, right, this value, the last value. So we can use b minus a divided by 3, so we will get p. Okay, so we can do it in here. So we need to define, okay, define float, no, integer first, integer number of p, okay, number of p, okay, let's say it is 100, okay, it is 100, and then we can calculate float, okay, p is equal to b minus a, right, divide by 100. Okay, so this is how we calculate p, right? So p, now we can calculate, now we want to get the values, okay, we want to get the values for x1, xi plus 1, blah blah until b here, right? So we need to get the value for this x, and then for each x we need to get the value, okay, for y. Okay, we need to get the value for the value of y for each x here. Okay, so that we can use these x and y values to calculate the trapeziums. Okay, so to do that we need to use for loop, okay, and then we need to use nested for loop as well, okay, to do the integration. Okay, if we see from here, okay, let's see how many xi's we will need. Okay, how many x values we will need. So if we have defined 3 trapeziums, we'll be having 3 plus 1 numbers of x, right? So if we see we have 3 trapeziums here, and then we have 1 value of x, 2, 3, and 4. Okay, and then for each x we have its dependent variable y, right? So we will have total 4 x and 4 y's. Okay, let's say if we have 100 trapeziums here, then we'll be having 101 x and 101 y. Okay, so there's always one extra, okay, for x and y values. So this one, okay, so we need to use array, okay, array for x, okay, so number of p, that's number of trapezium, okay, so we have 100. Now the value for number of x that we'll be having is 101. Okay, we always have one extra, okay, compared with number of trapezium. Okay, float x 101, okay, and float y, okay, 101. Okay, so we need to calculate the value for x, right, for each x. So x starts from a, okay, and then the second value is a, the x0 plus p, right, and then the third x, okay, you see from here, so this value x0, okay, let's define this value here. The first value of x is x0, okay, so the x0, the value is a, right, then the second value x1, 0 plus 1 is 1, right, so x1, okay, is x0 plus p, right, and then x2 is x1 plus p, okay. So in programming we can do it this way. For I, integer I starts from 0, okay, I less than equal to num p, okay, I plus, right, your xi, okay, the ith value of x is equal to a plus I times p, right, okay. So if you look at the logic here, okay, so a is the first value, okay, so this one is 1p times, is 1 times p, right, plus a. So this one, okay, when it comes here, this x, the second value is this one times 2p, right, and this value here is this one x plus 3 times the p. Okay, now because we have 3 p's here, okay, so this is how you program it in to get what is that, the ith number of x, okay. So this one is for xi, okay, and then for y, okay, for y, okay, it's slightly complicated, okay, for y, okay. So for y, so we need to do it this way, okay, it's a nested loop, okay, to get the value for y. So for, okay, integer j starts from 0, okay, j less than or equal to degree, and j plus, okay. So your yi is actually equal to a j times a j times oh, actually it's plus like that, okay. So your yi starts from 0, okay, your yi starts from 0, okay, times power xi and I. Okay. Hold on, xi times j, sorry. Okay. So this part this part is actually your polynomial, right? So your polynomial, okay, so if you have a 3-degree polynomial, okay, then you have a for loop, okay, y starts from 0, okay, this one plus this one plus this one, okay, so the 0th loop, okay, the first loop, the first loop when when j is equal to 0, so your y is actually a0, okay, and then in the second loop plus a1 times x1, okay, plus a2 times x2 x square plus a3 x cubed, and so on. Okay, so that part, okay, is here. Okay, so you have to initialize yi is 0. Okay, we have 101 x, so we will have 101 y. Okay, and then for each y, okay, for each y we need to look through the, what is that, the coefficient, okay, from j 0 to the, what is that, number of degree of that polynomial. Okay, so this is what it means here, so this part, right? So from here, so we get the value for each y, right? So we'll get the y for this guy, this is y0, this is y1, this is y2, and this is y3, and so on. Okay, so this is how it works. Okay, and then we have done halfway doing this part. Okay, do integration. So do integration. Okay, we can further refine the steps here. Okay, so do integration. Okay, so the first step. Okay, first step we can get xi and yi. Okay, and then the second step, okay, you can say calculate trapezium I, okay, and then third, okay, then you can sum all trapezium I, okay, you sum them out, then you get the integration. Okay, so we've done the first part here. Okay, get xi and yi. Now we want to calculate the trapezium. Okay, so still remember we have 100 trapeziums. Okay, number of p. Okay, number of trapezium. So for total number of trapezium we have 100. So we need to define an array to hold 100 numbers, right? So to hold that 100 numbers, so we need to use float. Okay, and then trapezium, okay, and then that is 100. Okay, and then you need to use for loop. Okay, integer I starts from 0. Okay, then I less than number of p. Okay, and then I plus. Okay, and then for the trapezium, you need to calculate the area. Okay, the trapezium area is calculated using this equation. Okay, 1/2 the width, okay, times the shorter edge plus the longer edge. So in this case, h, okay, h, the width is p. Okay, and then shorter edge, longer edge. So shorter edge is yi plus 1. Okay, longer edge is yi plus 1. So this one, trapezium, the ith number of trapezium is equal to 1/2, that's 0.5 times p, okay, times shorter edge yi, okay, plus longer edge yi plus 1. Okay, now we look through the, what is that, the equation. We look through the, what is that, the equation. We'll get 100. We'll get the area for 100 trapeziums. Okay, yi, so this one you don't need to worry about it. Is it yi plus 1? Yes. Okay, so it's correct. So the next thing is, once you have got the trapezium area, you want to sum them up. Okay, you want to sum them up, so you need to use float. Okay, sum, okay, is equal to 0. You initialize sum is equal to 0, and then you look through for I and t. I is equal to 0. Okay, I less than 100, I less than num p. Okay, num p, and then I plus plus. Okay, and then sum plus equal to trapezium I. Right. Okay, so you sum trapezium from 0, the first trapezium to the last trapezium. Okay, and then you get the total area under the curve. Okay, then you print out the result, C out. Okay, area under the curve is this one. Okay, sum. Okay, so let's run the program. Let's run the program and see what we get. So define degree of polynomial. Okay, I'll start with second degree. The first value for a is 1, second is 2, third is 3. You want to integrate from 0.5 to 1.5, let's say. Okay, so area under the curve is 6.25005. Okay, so we want, so how to say, we want to make sure that all the equations we use here are correct. Okay, we need to do validation. So to do validation, we need to do what is that, a bit of manual calculation here. Okay, so we can see that what is that, the, okay, if I do it here, okay, the integration for the integration, okay, I'll use this one. Okay, black, great. Right, so I have y is equal to, okay, 1 plus 2x plus 3x squared. 1 plus 2x plus 3x squared. Okay, and then I want to integrate y, okay, from what is that, 0.5 to 1.5, right? dx, I will get x plus x squared, correct? Plus x to the power of 3. Okay, so this one is from 0.5 to 1.5. Okay, so if you hit the calculator, okay, let's bring up the calculator here. Calculator. Okay, we need to check whether we've got the correct answer. standard, the one standard, I want scientific, right? So we will have 1.5 plus 1.5 square plus 1.5 cube, right, minus 0.5 plus 0.5 square. No, I have to, how to say this one? No way. Oh, never mind. Okay, we'll start again. 1.5 plus 1.5 square plus 1.5 cube, okay, minus 0.5 plus 0.5 square plus 0.5 0.5 cube, right? I will get hold on, 1 square.
So your formula is wrong, right?
Which one? This one.
The integrate one.
This one is wrong.
I mean the x plus x squared plus x cubed.
This one, yes. So what is the correct one? I don't remember.
Because if you integrate, you need to x power 2 divided by 2 and then x power 3 divided by 3.
X power.
Yeah.
Correct.
You need to divide by the degree of the x.
So this one, x2 divided by 2. So I'll get x. So I'll get x squared, isn't it? Oh, so this one should be, what's that, 3 over 2. Okay, what is that? Come again, come again. Okay, you give me the integration for this one, please. X plus x squared divided by 2. Then what about this? What about this 2? Cancel out, right? Okay, then this one is cancel out, right? Then should be getting x plus x squared plus x power 3, right? So I'm integrating from 0.5 to 1.5, right? So I'm actually correct, right? So it's a 0.875. Okay, but then this one is giving me 6.25. How come I got 6.25005 here? Okay, so clearly something is wrong. So we will need to go back and check our code. Okay, what is wrong? What is wrong? Right. So we have to check one by one. P. Okay, so 100 starts from 0. Okay, P, this one plus this one. Right, this one. If I go back to this one, okay. So if you look at this answer, okay, so the actual integration you'll be getting is 6.25, correct? But this one, okay, with our integration, numerical integration, okay, we get 6.25005. Okay, so that's with 100 trapezium. Okay, what if we increase the number of trapezium to 200? Okay, so 200. Okay, let's put it 200. This one 200. I'll make my life easier. Put it on P. Okay, and then this one X will become 201, 201. Okay, so float trapezium will become 200 as well. Okay, now if we run the program again, I don't want to print out this one anymore. Let's remove it. Okay, if we run the program again, okay, degree of polynomial is 2, 1, 2, and 3, range from 0.5 to 1.5. Okay, now you see, okay, I'm getting closer to the actual value, right? So if you keep increasing the number of trapezium used, okay, in integration, you get more accurate answers. Okay, so choosing the number of our trapezium in numerical integration is extremely important. Okay, but this since this is very small, okay, so 200 or 100 number of trapeziums is all right. Okay, because what's that, the error, the percentage error is extremely small, so it's like 0.0001 divided by 6, right? So it's like nothing. Okay, the percentage error. Okay, so this is numerical integration, okay, for using C++. Okay, I hope you enjoyed the what is that, the lecture. Okay, questions?